So the work that I'm presenting, it's a very tight collaboration with Dan and Chandra, who are in the audience, and the systems we are evaluating were built by a large team of engineers. Now, cloud applications are changing continuously, and for each change, we need to, of course, make sure that it's correct by testing it, but then before we deploy it to our billions of users, we need to deploy it to a small partition of the users to make sure that this change doesn't degrade anything, particularly performance. Now, when we deploy it to a small partition of the users, we need to make sure that we exercise that partition with representative load, because that's the only way we can get a clear answer on whether the change is detrimental. So when we think about representative load, the simplest manifestation of load is queries per second. Given that our users are global, and during the day they're awake and they're doing certain things with their applications, and during night they're asleep and are perhaps less active in our systems, we expect that the queries per second for our users will change over the course of the day and over the course of the week as they wake and as they sleep. So that's the expectation. Now, does this expectation actually hold? This graph shows you the queries per second for a component of Gmail, and it's scaled so that it's divided by a constant over the course of a week, starting on a Sunday and going till a Saturday. As we had expected, the queries per second changes over time. However, contrary to our expectations, the change is anything but smooth. We see these extreme spikes and we see these extreme sharp dips. Why is this happening? Now, even though the QPS is changing, given that we are serving large numbers of users, we expect that at least the mix of requests does not change. In other words, the mix stays on the average constant. So let's explore this expectation. To quantify a mix, we use the average response size for a user request. Now, if the users are in aggregate making the same requests over the course of the week and over the course of the day, we expect the average response size to be nice and flat. Instead, we see that the average response size varies by up to a factor of 2 over the course of the week. So not just the QPS changes, but the actual mix of requests also changes. Why is this happening? To understand this at the very first level, we need to recognize that our systems serve user-visible requests, which are requests generated by the user or their devices, and it also serves non-user visible requests. And these are requests that our system does for essential work. It's essential work, but it's not time critical. It can be delayed. An example of such work is checking the invariance of our data. Because we have such a large amount of data, we continually check it to make sure that there are no invariants in our data that are violated. As you might expect, the user visible requests have a higher priority, and so as a result, the user visible requests effectively throttle the non-user visible requests, resulting in a changing mixture. Let's take a look at data to see how that actually happens. This graph shows you the CPU usage of user visible requests and non-user visible requests. The green dashed line at the bottom are user visible requests. And you can see that follows the nice diurnal pattern. The red line is non-user visible requests, and you can see that has wild changes. There are 2 points about this graph that are interesting for our mix. The first is when the user visible requests are high, they're at a peak, the non-user visible requests are at a trough. And when the user visible requests are at a trough, the non-user visible requests are at a peak. This is by design. But one of the consequences is that in the 2 points that I have marked on this graph, we are going to get a very different mixture of requests to our system. Okay, so now that we understand why our request mixture was changing, we might have this expectation that at least if we look in each category separately, we just look at user visible requests, or we just look at non-user visible requests, well, things should be pretty flat there, right? Yeah. Let's start by looking at user visible requests. In this graph, on the left axis, the blue line shows the queries per second for usable visible requests, and the red line on the right axis shows the bytes per request, so the mix of these user visible requests. While we see that the user visible request mix does not change as wildly as before, so it doesn't change by a factor of 2, it still changes by 20% or more. And of course, you might be wondering why this happens, and one possible intuition is that during the day, users are accessing the system with their laptops and their desktops, and at night, they're not doing that, but their phones are still syncing to our servers. So as you can imagine, between the day and night, our request mix will change. Let's take a look now at the non-user visible requests. Unfortunately, it turns out that the non-user visible requests are even less predictable. And the reason for that is that they incorporate a lot of one-off events. So for example, about a year and a half ago, there was an event where there were 4 lightning strikes on a single data center in Belgium. And as you might imagine, that poor data center keeled over. And that data center was serving Gmail requests. And Gmail is designed so that users experience no degradation at all. However, what that meant was that because that one data center was down, the users that had a copy of their data in that data center now had one fewer copy available. So potentially there was a danger of degraded availability for those users. To mitigate that, our system automatically went into a mode where it started reconstructing the additional copy that we had lost on other data centers. And as a result, the non-user visible requests, they increased, as you can see in the circle area, over the course of next several days while we recovered from this data center outage. So non-user visible requests are even worse. All right, so now that hopefully I have convinced you that our load is changing continuously over time, and it is going to be super hard for us to say, compare one point in time to another point in time, or one day to another day, because they are just going to be different requests. So what we have to do is to do same time comparison. So in other words, have an experiment where there's a test and a control, and we compare them only at the same points in time. And we hope that if you pick a large enough test and a large enough control, that we will get statistically significant results. That's what we expect. This graph shows you such an experiment. In this graph, rather than picking different test and control in this graph represent running exactly the same code and exactly the same configuration for 100,000 users each, active users. And this graph shows you the scale latency at the 50th, 95th, and 99th percentile. Now, given that these partitions are identical code, and we are doing same time comparisons, we expect the dashed lines and the solid lines to perfectly line up. We do not see that. In particular, we see that for the 95th percentile, the test and control vary by as much as 50%. So clearly, 100,000 samples is not large enough to capture the difference between our users. When we look at 10 plus million samples, so 10 plus million users in each partition, we now see that the dashed and the solid lines effectively line up, And so now we are able to, with this kind of an experiment with tens of millions of users, detect small 1% changes in performance. So now that we have a means of detecting a regression, the next problem is, you have a regression, how do you debug it? How do you figure out what was the cause of this regression? In order to do that, we find that we need to rely on two kinds of contexts, the operational context and the temporal context. Let's look at the operational context first. In this example, let's suppose that our system runs on 3 machines. As you may imagine, it runs on a lot more than that, but just for the illustration. And each color represents a single operation. So as you can see, for example, the pink, the reddish color, that operation has parts running on all 3 machines, communicating via RPC calls. Now the operation context for the pink operation is simply all the parts of that operation, no matter what machine they are running on. So it's everything about that operation, so that you can answer all the questions about why the operation is doing what it is doing. Now, operational context in our environment, getting it even for a single process is hard. Forget about these RPC calls and multiple processes. And there are prior approaches to dealing with this. So imagine you have a single process, and as you can expect, the single process itself has many layers in it for libraries and such. The common approach for doing this is to insert probes into each of the layers, so thermometers in each of the layers, and then pass a token down the stack. And all logging at each layer labels that log entry with the token. So in that way, when we look at the traces from each layer, we can join them together using the token as the join key. And once we do that, we can now get the operational context, because we can combine all the bits and pieces for a particular operation. Now this approach is quite problematic for 2 reasons. First of all, we need to maintain and record the token across all of the layers, and not all of the layers might be maintained by us. Some of them might be libraries that we don't even have the code for. Furthermore, we don't want to go and do this propagation in the kernel, because the kernel is a complex piece of code. We do not want to make a mistake there and take down all of Google. So this approach will not work very well if we want to combine this information with kernel information. So specifically, we cannot, with this information, conveniently look at a kernel event and attribute it to the appropriate high-level event. The approach that we use is called vertical context injection. It's a simple idea. The idea is that for each process, we collect these traces at the lowest level, at the kernel level, and they are standard off-the-shelf mechanisms such as ftrace for collecting kernel traces. Then what we do is that each layer injects its information into the kernel trace. So in other words, all we need is a kernel trace. All the other information has been injected into it. How do we inject information to the kernel trace? The way we do that is by making system calls. Any system calls we make at any layer, they will get recorded in the kernel trace. If the system calls are stylized enough, we can actually look at the kernel trace, do the pattern matching, and recognize the high-level events that would cause that particular stylized sequence of system calls. So here, let me show you, so that's how it works. So this is an example of how it works. So here we have a stylized sequence of 2 system calls. They are both calling get PID, which is getting the process ID. It's an innocuous system call. It doesn't do anything. It actually doesn't take an argument, but if you pass it an argument, the kernel tracing mechanism records it. The first system call says, I'm about to start a high-level operation. And the second system call says, it's for the read operation. So when we see this to event in the kernel trace, we know that all the operations on that thread are on behalf of the read high-level operation. And then when there's a context switch, it cannot be the read operation anymore because it's some other thread. It's doing something else. Now on the second thread, we might see the same pattern of system calls, and this time to mark the start of the blue operation. And so now we know that everything on the second thread is on behalf of the blue operation. And so on and so forth. You get the idea. So using this approach, we are able to take all the kernel events and color them with the appropriate high-level information, be it RPCs or lock contention. So we can do this. Now, this has been a very useful mechanism for us. So let me give you one example of how we have used it. So when we rolled out a particular change, we noticed that our processes were getting throttled with respect to CPU. So they were using a lot more CPU than they were using before. When we looked at the kernel traces, we indeed saw short bursts of high CPU usage, but we did not know what was causing the high CPU usage. When we did the vertical context trace injection, we were able to figure out exactly what the high-level event was. And specifically what was happening was that whenever we serve a user request, we read some small attributes about the user to serve that request. And rather than reading them all in one call, we were making lots of small calls. And it was this thundering herd of small requests that was resulting in a burst of CPU usage and thus resulting in throttling. So now that we have talked about the temporal context, operational context, let me tell you about the temporal context. Now, as you can imagine, sometimes our requests might be slow, not because of something that they do, but something that appears to be happening around the same time. So the temporal context simply collects all the information around the events of interest. A typical way of doing this is to use Bursty Tracing. And the idea of Bursty Tracing is that you do sampling, but when you do a sample, you don't collect a single event, you collect a burst of events. So let's see what this means in this example. So let's suppose this red box is making a request to the blue box, and it turns on bursty sampling. So it gets 2 red items sampled, and then 2 not sampled, and then 2 sampled. Now a green box may also be making requests. Remember, our systems are made of lots of processes that communicate. And it will also do some sampling like this. Unfortunately, because the counts are maintained independently by our processes, these samples will not necessarily be coordinated. So we will not be able to collect all the information around a pink event of interest. So what we need to do is we need to coordinate our bursts. And specifically, ideally, we would like to be able to collect a burst of duration 2 to the d milliseconds every 2 to the p milliseconds. We have found a very compact encoding for doing that. Effectively, we construct a bit mask where the lower d bits are all zeros and the upper p minus d bits are all ones. And then to determine if we should sample a particular event, we take the current time in milliseconds and we apply this mask to it and check to see if the bitwise AND is the same as the mask. If it is, then we sample, otherwise we do not. So as an example, if our mask is 11100, it will cause us to do a burst of 4 milliseconds every 32 milliseconds. So using this and using the clocks on the machine, we can coordinate these bursts. So with coordinated bursty tracing, all we need to do is pass a mask to all of the processes of interest. They all are coordinated because of the time, and we end up getting the temporal context to analyze for our system. All right. So I'm out of time, so I will go just to the summary, and I will give you examples later. So to summarize, for meaningful performance experiments, hopefully I've convinced you that we need to do experiments in production. To reproduce our complex workload in a test environment is very hard. We need to do controlled A/B tests with tens of millions of users. We need to do long-lived tests because our requests are changing continually. So if you do it for a short period of time, we are not going to capture the full variation. And finally, because we are collecting data from production, we need to be very careful and we need to be very efficient. So we need to have creative ways of collecting this data. So thank you all for staying, and come and talk to us if you would like to hear more stories. Thank you.
Hi, I'm Heidi from UIUC. I have a question about your kernel tracing. So one of the biggest problems when you are tracing something in kernel is where to store your tracing data and how not to mess up everything else, like not to slow down the whole system just because you are messing with kernel memory. How did you manage that?
Yeah, so what we do is our kernel traces are collected in an in-memory buffer. And the buffer is large enough that we can collect about 10 seconds of kernel trace before the buffer runs out. And so this is another place where the coordinated bursty tracing is useful, because we can turn it on for a burst and then we can turn it off. In terms of messing things up, you're talking about the observer effect. We find that our kernel tracing mechanism adds less than 3% overhead. But even with that, there's always a theoretical possibility that you have perturbed your system by measuring it. And so we always close the loop. So once we find that we have a cause or an explanation for a problem, we then do an intervention based on that understanding and then run another experiment to make sure that the intervention has the appropriate effect. In practice, I think there's only one case I can think of where the observer effect actually hit us. Thanks.
Hi, great talk and great work. Ajay Mahindra from AT&T. I have at least two questions. The first one is around the test versus control. So you mentioned that different regions or different locations have different characteristics of traffic. So I wonder how this control group are selected, right? Because even if you look at, say, US, there are 4 time zones, right? So if you try to take the East Coast versus West Coast, you'll see different diurnal patterns, right? So
yes.
When you're trying to evaluate a change, specifically for A/B testing, how do you try to pick the control? That's my first question.
So I think that in the distant past, we tried to be very clever about it and tried to be very careful with the populations. We realized that no matter how smart we were, our users were always more diverse than our intelligence levels. And so what we do now is that we do random sampling. So in other words, in a partition that we take, say of 10 million users, there will be people from all over the world just mixed in, randomly selected. Now, it is the case that our diurnal cycle looks a little bit funny, right, for that reason. But it basically is a random sampling of all the users.
Okay. Second question is around how long do you do this A/B testing as you roll out the new change, right? Because as you are covering the whole group of users, your control set size is decreasing. Right?
That's correct.
So if early on you have a smaller test and a larger control. But as you're reaching the end of the deployment cycle, you have a much larger test and a much smaller control.
So we make sure that our control and tests are very similar to each other in size. And as a matter of fact, we pick the test and control in the same data center, because different data centers might use slightly different generations of machines, so we don't want to perturb based on that. So what we'll do is when we want to do an experiment, we'll pick a test and a control both in the same data center, tens of millions of users each, run it for about a week to make sure that we see at least the weekly cycle. Occasionally, if we are worried about particular one-off events causing issues, we might even manually trigger those one-off events to tickle our system. And then once we are happy that this test is fine, then we will gradually roll it out to all the users, each time maintaining a control.
Okay. Thank you.
Yeah.
Hi, Rodrigo Fonseca from Brown. Very cool talk, very nice tricks. So one question, the context injection that you do with the kernel traces, can't tell all the whole story, right? Because you showed that the operational context is spanning several machines.
Yes.
So what's the rest of the story? How do you actually get the context correlated across the machines?
Very good point. So basically, we use a Google system called Dapper, which there's a paper on that out there. And what Dapper does is that it gives us the RPC level information across the machines. And then within a machine, we can do vertical context injection.
Right, so you're just pushing the Dapper information
Exactly.
down. Cool.
Additionally, we can actually combine this with coordinated bursty tracing to use Dapper sampling using the coordinated bursts.
All right, thank you.
Yeah.
Ran out of chocolate?
Yeah, thanks everyone. Now, with that, we'll end the session. I do have the chocolate here, so anyone who asked questions can please stop by and collect it. Yeah. Okay, thank you.